So Kepler's second law, I'm actually going to have to go back to the previous diagram to actually show Kepler's second law because I kind of parsed it, but here's actually a somewhat formal way of describing it. So going back to how it was defined before, the radius vector of the parent star to the planet sweeps at equal areas at equal time intervals. So what that means is if you go back to here to this diagram, uh, let's say that going from here, this is time t1, and this time here will be t2. So this is where the Earth is at the second time. So if we consider the sort of angle between here, say alpha, then during the same time interval, or this arc, so that arc will be traced over here. It's not necessarily great to scale, but here's t3. So for Kepler's second law, t2 minus t1 is equal to t3 minus t2. And obviously you can do some rearranging if you want to say 2t2 is t3 minus t1 or whatever. Although this angle here will be different. So the angle is here. Uh, this angle will be something like beta. The arc is what's constant, and the ratio of the distance traveled and the time taken to travel is a constant value. Uh, just note the radius vector. So this here is a radius vector. Here's another radius vector. So all the things in green will be sample radius vectors. And it sweeps out equal arc lengths at equal times or areas. Um, they essentially can be parsed to mean the same thing in ellipses anyway. So it relates to angular momentum and conservation of angular momentum, which we've discussed before. In a way, the um, length of the arc is inversely proportional to the radius, and it's also proportional to the velocity. So this means that as the radius decreases along the bits of the ellipse that are most squished, the velocity steadily increases. And here as well, the closest distance will be is known as the perihelion, and the furthest is known as the aphelion. Again, just something to be noted.